we ready to go?
It says video unavailable for some reason. Just a second. Are you sharing? You're sharing your screen, right?
Yes. Can
Maybe
people
you're
see it?
sharing.
Yeah, we can see everything, Emil.
We can see everything, but not on, it doesn't go to YouTube for some reason.
Is that it? Could be because you've got a bad link or bad Wi-Fi.
Uh, let's see if I'm spotlighting Emil. No. Uh, yeah, let me stop and start again. I don't know why it's doing that. Or it
It
could be that
says
Emil.
it says YouTube on my screen.
Yes, it's just that I mean, just on the YouTube site it says video unavailable. So ah. Oh no, it's working. On the other one, it's working. Okay, perfect. Yeah, let me stop and start again. No, it's okay. It's all done. Or it
It
could be that
says it says
You're
it's
replaying
perfect. The
yourself,
YouTube
yeah.
is working.
Yeah, Joseph, you're having a conversation with yourself. I think you're replaying.
I know it was the YouTube which recorded me. So
Okay.
okay, so we're very happy to have Emil. He'll be telling us about fiber and stars and BTC black holes.
all right. Well, thanks for the invitation. Sorry I can't be there in person, but hopefully this is the next best thing. So what I'd like to talk about today is some work that I've been doing with Yoav Zikdon uh, at Cambridge, which is about to appear maybe next month, and is a continuation of a series of works we've been doing over the last couple of years. I talked about the third in that sequence of works at the last meeting a year ago. And so this is, in some respects, a follow-up and an elaboration um, of that talk. So what are we going to do? We're going to study three charge BPS states in type 2 string theory in the frame where the BPS charges are NS fibranes, strings, fundamental strings, and momentum. And why am I interested in that particular duality frame? Because the Nivy-Schwarz fibrane is one of the heaviest sort of solitonic objects in string theory. It's the magnetic dual of the fundamental string, and its large tension means that it has a classical back reaction. And so we'll be very much interested in, so you can't study Nivy-Schwarz fibranes in string theory without studying their back reaction. And so it's a good place to be because you have these heavy objects and they can make things that look like black holes, as we'll see. Um, our so last year I talked about the properties of typical half BPS states. This talk will be about the properties of typical quarter BPS states, and those include the superstrata that many in this audience are familiar with. Okay. In the course of the discussion, we'll be meeting a variety of strings. So here's um, a playbill so you can keep them straight. So of course, there's the fundamental string. It will be one of the BPS charges that we'll incorporate into the background. There will be the NS5 brane, which if you wrap it on, so we'll be wrapping everything and dimensionally reducing on some compactification T4. And if we wrap the fibranes on T4 and dimensionally reduce to 6 dimensions, now the fibrane becomes a string in 6 dimensions. It's magnetically charged, so there's a string-string duality in 6 dimensions because the strings couple to a three-form potential and fibranes couple to its magnetic dual. And so the fibranes are the natural magnetically dual. They're like the analog of a magnetic monopole, except now it's a magnetic string. And then at some point, I won't have much to say about it. There is another kind of string, which is called the little string, living inside the fibrane. It is the natural um, constituent of non-abelian dynamics of fibranes. And it's can be and black fibrane thermodynamics can be viewed as the analog of the deconfined phase of n equals 4 Yang mills in the ADS5 case. It's the natural object whose liberation explains the thermodynamics of black fibranes. Okay. Now, if we study fibranes on their own, they source a simple background, which if we just don't excite them at all, we just have, in some sense, the five-brane vacuum. Then we get a metric which has a warp factor in front of the transverse geometry. So the transverse geometry is a warped R4 with a harmonic function, which is governed by the positions of the fibranes. And similarly, the dilaton sources is sourced by the five-brane harmonic function. Okay. Now, if I was in asymptotically flat space, I probably should have put a 1 in the harmonic function. Much of the time, we'll be interested in the decoupling limit, where we scale the five-brane separation to 0 in proportion to the string coupling, so that there's some rescale coordinates where this coupling disappears, and the dilaton is just governed by where you are in the five-brane throat. Okay. But the key point is that if we put all the fibranes on top of each other, then we're in this domain of little string theory where there are light non-abelian magnetic string excitations living inside the fibrane. And that theory is hopelessly complicated in the infrared. And so if we want something that is a smooth capped geometry, we should pull the fibranes apart a little bit. And I talked about this extensively last year. I refer you to that talk if you want more details. But basically, the idea is that if we separate the fibranes apart a little bit, string theory doesn't see this geometry, okay? Because strings have a natural size. They have a size alpha prime. And so if you dive way down this throat, if you try to put the string at some position X, which is extremely close to one of the fibranes, so that you're in some sense diving down some kind of five-brane throat of a single five-brane, the problem is that the natural width of the string wave function is such that the string doesn't fit down this throat. It's in some sense too big, too fat. And so perturbative string theory can never visit this region way down this throat close to the fibranes. And so what perturbative strings see is not this geometry, which is what you would literally read from what's written above. String theory instead sees some kind of nice, smooth, capped throat, where the scale of the cap is determined by the separation of the fibranes. And the size of the dilaton, the maximum value that the dilaton can attain, as seen by perturbative strings, is again governed by the separation of the fibranes. And so this is something that one sees in exact worldsheet solutions, where the positions of the fibranes are in some nice symmetric array. Um, but beyond that, one can argue on the basis of the properties of those exact solutions that if you take such a smooth cap throat and you now start moving the fibranes around and say bring two of them close to one another. Okay, so we have a bunch of fibranes, separated apart, but then we bring two of them close together. Then what happens is that you have a little throat whose size is not now L string, it's root 2 L string. And it turns out that's big enough that even with the size of strings, they can still fit down such a throat. And so what you'll see is a throat whose size is like root 2 L string, and then a bunch of other single throats whose size is of order L string. And strings can fit down this throat, but they can't fit down this throat. Okay, so anytime you push two fibranes together, string theory sees a strong coupling singularity. But as long as you keep them apart, everything's fine. And so what one will find is that smooth cap geometries are related to being slightly onto the Coulomb branch of fibranes, where they're sufficiently separated that the string theory is weakly coupled and the geometry is smooth on the string scale. Okay. So now let's add the next charge in our menu of charges. So we're going to take the fibrane, we're going to compactify it on a 5 torus. We'll single out one of the directions on the 5 torus to be special, call it S1Y. And we'll twist the fibranes so that there are periodic boundary conditions on S1Y. Okay, so here's the Y direction. Um, okay, so we're going to wrap N5 fibranes into a single fibrane by giving it some twisted periodic boundary condition. So in some sense, our magnetic string will have winding number N5. Okay, and then we'll put momentum on that string. Okay. Why do we want to put momentum? Well, if we don't put momentum, then the string um, shortens itself by bringing all the strands together, and then we, get back into this strong coupling problem. If we give the strands of the fibrane some momentum waves in the scalars that describe where they are in the transverse space, then self-consistently, the excitation of the string keeps the strands of the fibranes apart. So you get a self-consistently separated, Coulomb branch separated collection of fibranes that are prevented from visiting one another by the fact that they carry these momentum excitations. And of course, we can always do the same thing with strings. And so one of the other actors in our play will be a set of profile functions that describe where a wiggly string is in its transverse space in 6 dimensions. Okay. Now, all of this is governed by some effective action, which is supergravity coupled to some world volume action for fibranes and world volume action for fundamental strings, which is, of course, just the natural Polyakov action for a fundamental string. Now, when we compactify the fibranes on T4, as I was saying before, they're magnetic strings in 6 dimensions. And so we can write their effective action again in the Polyakov form, where now the fibrane is coupling in the same way that the fundamental string does, but now to the magnetic dual 6-form potential. Again, dimensionally reduced on T4 is a 2-form potential, which can couple then to the magnetic string in the usual Polyakov way. And of course, the effective metric that's seen by the fibrane differs from the metric seen by fundamental strings because the tension of the fibrane involves a 1 over G string squared. Okay. Now, we're going to look for quarter BPS solutions of the field equations that we get by varying this joint effective action with respect to the fields. Right, so we'll get a set of brane embedding equations, which are going to be the standard equations of motion of strings. And then we'll get a collection of supergravity field equations that will then, when we vary with respect to the supergravity fields, we'll have explicit string and fibrane sources. Okay, and the form of the solution we'll be looking for the bulk fields is the standard quarter BPS ansatz that we've known about for more than 20 years, where their solution is written in terms of harmonic functions. So there's a harmonic function for strings, there's a harmonic function that we've already introduced for the fibranes. There's a harmonic function which carries the momentum that is carried by the sources. And then there are various harmonic forms, omega, beta. There are harmonic forms that code the magnetic flux carried by the fibranes and carried by the strings. And it's important to remember that B2 and B6 are not independent, but they're electrically magnetically dual potentials. In the presence of both fibrane and string sources, the poles in the harmonic function Z2 are trying to make the string coupling stronger. The strings are trying to do the opposite, make the coupling weaker. And somewhere in deep into the geometry, these two will reach some kind of natural détente where the string coupling saturates. And again, one's looking for that coupling in the cap of the geometry to be weak so that the whole solution is self-consistently perturbative in string theory. By the way, slow me down with questions if you have any. Okay. So, as I said, we vary the effective action with this ansatz for the geometry and try to go solve the field equations. And we were most of the way through that exercise with Yoav when Yosef told us that it's already done. So there's a nice paper from 2012 by Nick and his students at the time, where they wrote down the form of the solution in the standard way for this class of geometries, where you order the equations in some hierarchy and solve them sequentially in what are called layers. And the first layer of that structure is to solve. There's among the supergravity field equations, I believe it's the dilaton equation, gives the harmonic function Z2, as I say, a harmonic function now with explicit sources given by the fibranes. And so that's solved by the sort of ansatz that I wrote down before. There's a similar harmonic equation for the corresponding magnetic dual potential Z1 that basically governs the redshift in the cap of the geometry, as opposed to Z2, which is governing the depth of the five-brane throat where it caps off. Okay. And those first layer equations are independent between the string and the five-brane sources. So the strings and the five-branes don't talk to each other at this stage in the sequence of solving the field equations. There's also a set of harmonic two forms from which you read off the various harmonic forms that make their appearance in the anisymmetric tensor fields. Okay, and so they have a somewhat similar structure. Okay, where again the string and five-brane sources don't talk to each other. So either there's a harmonic function that knows about where the five-branes are or where the strings are, but again they don't talk to each other. Okay. And then you come to a set of field equations where uh, the sources do start talking to each other. So, for instance, if we look uh, at the harmonic function that carries the momentum in the solution, okay, that's a basic harmonic equation. And what are the sources? Well, the sources are some explicit. Well, it's the momentum carried, by the brane sources. So it's going to have a term which is just the energy momentum tensor on the five-brane magnetic string and the energy momentum tensor on the electric string. That is delta function located where the strings and the five-branes are. Okay, but they have a coefficient. So the string source has a coefficient governed by the five-brane harmonic function that we've already solved for. And the five-brane momentum source has a coefficient, which is the string harmonic function that we already solved for. And then there are bulk sources, which are interactions in the bulk between the anisymmetric tensor fields and interactions between the harmonic functions of the strings and five-branes. Okay, and so then that leads to a solution, which, as I say, Nick and friends helpfully gave us already. Where these quantities R and R tilde are just shorthand for these separations. You're looking for the solution at some generic point X in the transverse space. Okay, and so then it depends on systematically on these differences, which Nick and friends called R. So there's an R for the strings, there's an R tilde for the fibranes, and you see those quantities appearing all over the place in the solutions. Okay. There's also, they gave the solution for the last harmonic form omega, which carries one of the angular momenta of the solution. And now, where do we depart from what Nick and friends did? Well, they were interested in finding some solutions where each of the sources was an extremal black hole. So it's a M equals 0 BTZ black hole that you're just letting wiggle in the transfer space a little bit. Um, and so where we depart is that we don't want our solutions to be M equals 0 BTZ black holes because my claim is that those things have some strong coupling region down at the bottom of their throat. So instead, as I say, we're going to keep the sources self-consistently separated. And so we're either going to have NS5P or F1P. And so we take Nick's solution and we just turn off either the string charge or the fibrane charge on this on each of the source profiles.
Emil, I think
Yeah.
it's important to say that beta is equal to 0 on these solutions.
Yes. So I should have said, there's what's called a zeroth layer of BPS equations, which is choosing what is the transfer space in which all of these things live. Okay, so we're in 6 dimensions. So there's a T, which everybody has. There's a Y, which all the strings are wrapping. And then there are 4 more directions that are transverse to the electric and magnetic strings. And so the first step of this solution is deciding what is that transverse space. And so the simplest thing to do is to take it to be R4. Okay, and then one also has to supply some kind of self-dual harmonic one form that is a starting point in all of this. And one has the freedom to choose it to vanish for the class of solutions that we're looking at, which immensely simplifies the whole collection of BPS field equations. And so these are solutions which have a vanishing beta. Remember, beta is the one form that twists the Y circle over the V direction. Okay. Okay, and as I say, all of these solutions look like they have inside them all kinds of double pole singularities, even nastier singularities, maybe if the strings and fibranes were on top of each other. All of those are fakes, right? The fibranes are self-consistently separated. And as I said, strings don't see this geometry, where there are these, look like nasty poles in the harmonic functions, which are going to make some sort of curvature singularities. Strings don't see that because strings can't visit this region. Strings see this. Okay, so this whole geometry, as far as perturbative string theory is concerned, is kind of capped off at the scale of the separation of the fibranes. Unless you happen to arrange it so that 2 of the fibranes are coming close together, and then locally there will be some throat which is governed by the separation, some throat of size, root 2 L string, okay, whose depth is governed by the separation of those 2 particular fibranes or particular windings of the fibrane. Okay. And then, of course, there are poles in the harmonic functions for the strings, but those are just the usual, alpha prime effects, right? We're looking at classical solutions of strings, and really we should quantize the string. And when we quantize the string, it's fuzzy over a scale alpha prime. And so again, you don't really see this sort of geometry. You see some kind of cap geometry where you should smear the string source over a region of size alpha prime. Okay. So we have some solution, and we should, specify some collection of source profiles, X of V, F of V, etc. Okay, we're not interested. Okay, we might be interested in enumerating all of these things, and so that's certainly an exercise one can do. Um, uh, uh, Maybe slightly more interesting is to say, okay, what does the typical one of these things look like? And for that, uh, one might be interested in, these are harmonic functions governing all of these solutions, and harmonic functions obey a principle of linear superposition. So we can take our ensemble of string wiggly profiles, we can take our ensemble of fibrane wiggly profiles, and we can do an ensemble average. And this was the 2-charge version of this for NS5P sources was the subject of my talk at the last one of these conferences a year ago. And the result was actually something that was worked out actually long ago, starting with work of De Boer and collaborators almost 20 years ago, who said, "Oh, let's just, let's consider the maximally mixed state, right? Let's just uniformly average over all possible profiles, and what do we get?" And what they got was that the five-brane harmonic function was what you would expect at large R, which is namely, the double pole of the magnetic flux that's sourced by the five-branes. But then as you get to the scale of the five-brane separation, um, the geometry starts differing from that naive just uh, vacuum five-brane solution. Um, and what you see is that because the five-branes are spread out over some region of size R5, this double pole singularity starts getting a residue which is smaller and smaller. Why is it getting a residue that's smaller and smaller? Because you started diving inside the five-brane cloud. So a Gaussian three-sphere surrounds less three-form flux, and so the residue of the double pole should start decreasing. And indeed it does. And by the time you get to R equals 0, there's nothing left. You're inside all of the five-branes, and so the geometry just caps off smoothly. And the five-brane harmonic function just goes smoothly to a constant. What's the size of that cloud of five-branes? Well, you have a wiggly string. How big is a wiggly string? A wiggly string is a random walk. And so all you need to know is the number of steps in the random walk and the tension of the string, and I'll tell you the size. And so this is that size. The natural scale, the tension of the five-branes is the six-dimensional Planck scale. And then this is the number of steps in the random walk is the square root of the product of the momentum charge carried by the five-branes and the five-brane charge. And so if the number of steps is square root of this, then the size is the number of steps to the 1/2. And so N1 and P5 N5 to the 1/4 in units of the natural scale of the problem. Okay, so do the same thing for the strings and then ask, what does this geometry look like? And the answer is what you might expect. That is, if we ignore what's going on in the region of the source, then the geometry should look like the black five-brane solution carrying string and momentum charges. Okay, which if you take the five-brane decoupling limit, okay, where the five-brane linear dilaton throat extends all the way up to the UV. Then what you have is the linear dilaton throat of N5 five-branes. At some scale, which is governed by the charge radius of the fundamental strings, the geometry rolls over to this, region where we go back to the solution. Right now, when the constant in the one-brane harmonic function is no longer important and it starts looking like 1 over r squared, then the metric starts looking like r squared dt squared minus dt squared plus dy squared. So it starts looking like the t and y directions of ADS3. And so the geometry rolls over from linear dilaton to some ADS3 regime where the y circle starts shrinking from its asymptotic value Ry in proportion to the radial position. Then eventually, and so it's basically shrinking because you're starting to feel the back reaction of the strings, and the strings are exerting tension on the y circle. And so as you get closer and closer to the strings, that tension is bigger and bigger. And so the y circle, proper size of the y circle gets smaller and smaller. Eventually, you reach the moment. If you've arranged the hierarchy of charges in the appropriate way, you reach the charge radius governed by the momentum excitations. And then the momentum of the sources starts back reacting on the geometry, and the momentum is pressure, and the pressure is trying to keep the y circle puffed up. And so at some point you reach a balance between the tension of the strings and the momentum of the waves on the strings. And then you get an ADS2 region, or more precisely, the Y circle fibered over ADS2. And then, very deep in the geometry, it provided the sources, provided the charge radii, sorry, not the charge radii, provided the random walk radii of the strings and fibranes is deep down in this ADS2 region. You reach the scale at which, you actually start seeing the individual sources and the geometry caps off in a way which, as I've argued, is smooth as far as perturbative string theory is concerned. Okay. Um, And the size of the circle indeed is set by the competition between the momentum and the string charges. So the radius, the proper radius of the circle that the strings and fibranes are wrapping is NP over N1. So if you have, remember N1 times N5 times 6 is the central charge of the dual CFT in ADS CFT duality that's governing, the properties of this ADS3 region. Okay, now if you're looking at a state in that CFT, approximate CFT in the IR, where the momentum is sort of order the central charge for finite N5, um, uh, then the radius of this Y circle is self-consistently bigger than the string scale. There should be an L string squared here. There's an alpha prime. And so everything's self-consistently, perturbative in string theory, and everybody's happy, and you have a geometry that looks like BTZ or black five brane until you get to where the sources are, and then it caps off. Okay. But I would argue that what we're looking at here is not something that is a black hole microstate. What you're looking at is a five brane star. Okay, the reason why the geometry is capping off is that the actual depth of the throat for the black object is infinitely deep because it's BPS. Okay, and so the fact that it's capping off is telling you that the radius it's capping off at a radius which is governed by the radius of the sources. Okay, so you're in a situation which is exactly like the sun, right? Why is the sun not a black hole microstate? It's because it's way bigger than its Schwarzschild radius. Okay. This thing is capping off at a radius which is way bigger than the Schwarzschild radius. The Schwarzschild radius is, where an extremal horizon would be, and we're not at that scale. And so these things are better regarded, to my mind, as five brane stars and not microstates of BTZ black holes. This also, I think, is some variant of the sorts of things that Minwalla has been doing, right? We have a bunch of separated strings and fibranes, and they're all jostling around near one another. So, one could regard them as kindred spirits to that construction. Okay. So you have the situation that I was describing before where, okay, you have some ADS3 throat near in some, in sort of, this region of the geometry. And if the momentum charge is much bigger than the string winding charge of the sources, then you're in this situation where you roll over to an ADS2 region with the Y circle having a size in string units which is parametrically large. And so you trust the geometry. You're in the right duality frame to describe the infrared physics. If, on the other hand, the momentum charge is much, much less than the string winding charge, then at some scale well outside this ADS2 regime, the proper size of the Y circle dives below the string scale, and you're still well away from where the sources are, which is way down here. And so if you really want to describe the near source regime in the appropriate effective field theory frame, then you should do a T-duality from the NS5 F1 frame to the NS5 P frame. And that flips the role of the string and the winding and fundamental string winding and the momentum charges. And so while the original geometry that you started with in the UV is tracking onto something where you don't trust supergravity in the IR, there's a T-dual frame where that circle is now getting bigger and saturates at some big scale in the T-dual geometry. And of course, in perturbative string theory knows about T-duality, so this is nothing particularly exotic. It's just that you can't describe what's going on for this charge regime of BPS, quarter BPS states using supergravity. You can't trust supergravity in the frame which is appropriate to the asymptotic geometry. You need perturbative string theory to tell you about this region. Okay. So now I'm going to switch gears a little bit and talk about superstrata. So many people in this audience have been working diligently over the last 10 years or so, constructing large classes of exact solutions of the supergravity field equations, which carry these three charges. Well, okay, not these three charges. Everybody else likes to work in the D1, D5P frame. Um, and I'm um, an iconoclast, and I like to work in the NS5 F1P frame. Okay, and so the S dual of the superstratum solutions that everybody likes to construct are things that are carrying these three charges, except not quite these three charges. Okay, what does everybody do when they're solving these layered supergravity equations? They start with a string five grain supertube, and then they decorate it with momentum excitations. So what I've just told you about is not an NS5 F1 supertube that I've decorated with momentum carrying excitations. I've described for you a NS5P supertube, which is now augmented by by string sources carrying string winding and momentum. Okay. So you can think of what we're describing as some kind of gas of F1P, strings, some BPS strings, that are in some kind of cloud outside or intermixed with an NS5P supertube. But that's just T-dual to the superstratum. Okay. And so, this situation where I said it was actually necessary to do a T-duality to describe the near source region is exactly um, uh, the appropriate duality frame for describing superstrata in this regime of charges. So you start off with an NS5 F1 supertube, and then you decorate it with some momentum waves. Okay, well, by the time you get close enough to the source, you should really be working with NS5P supertubes decorated with winding strings. Okay, and Masaki Shigemori did an estimate of the number of such things and came up with an answer, which is the number of these NS5P supertubes augmented multiplicatively by the number of winding strings to the 1/4. Okay. Now, so far I haven't told you where the winding strings are relative to the five branes. I've sort of said, okay, well, it's some wiggly source, governed by some um, profile. Um, where are we? Yeah, some profile, you know, X of V. I didn't tell you what X of V is. In particular, I didn't tell you where the center of mass of these strings is. Okay, and so you could ask, okay, are they free to move around, right? Are these not bound, these strings? Can they fly off to infinity? Um, or are they somehow bound to the fibranes in some way so that I'm actually describing some bound state? Okay, and morally speaking, this is some kind of multi-center solution. And the history of this subject of multi-center BPS sources, again, is something that many in this audience are experts in. And the locations of these uh, momentum or string excitations that we're trying to put on top of the fibranes is governed by something that are called bubble equations that pin the location of the um, uh, cloud of additional BPS sources, fix their locations in terms of the quantum numbers that those things are carrying. So let me just sketch my current understanding of how that works in the present context. And I should mention that what I'm about to go through is province of some other work with other collaborators that is also virtual, but hopefully about to appear within the next month. Um, and so the analysis goes something like this. So let's let's think about the superstratum case as everybody else likes to think about it after you do the S duality. So where we have an NS5F1 supertube and we're going to decorate it with momentum sources. Now, the way people usually do this is they say, okay, uh, you know, the what we're going to do is we're going to modify the solution of the supergravity field equations by putting some wave sources in the supergravity fields. Right? Everybody's looking for horizon. I've sort of dodged all of that and saying I'm looking at things which actually have point sources. But if we want in this, the original spirit was we're going to look for horizonless, non-singular solutions of the supergravity field equations. So we're not going to put in any sources that are singular. We're just going to solve the bulk field equations and look for solutions which are self-consistently, non-singular and have no horizons and so on. So what you do is you say, okay, let's write down some waveform, some, delta, LMN, which are some wave profiles. And so you end up having to solve the wave equation in the supertube geometry, which for a generic source is hopelessly complicated. And so, one advantage of this explicit point source, wiggly profile ansatz is that you can be completely explicit about the generic solution as long as you're willing to accept the existence of the sources. But as I've argued, the existence of those sources is something that's effectively not singular in perturbative string theory. Okay. All right. And so in the superstratum ideology, you say, okay, let's start with this supertube and let's decorate it with momentum excitations. As I say, I don't want to go solve the wave equation in this geometry because it's a mess. What I'm instead going to do is I'm going to specialize the solution that I already have by dropping the F1, sorry, dropping the P excitation um, on the F1s. So they're just winding, okay? And to ease you into that, let's consider again the T-dual situation where this is an NS5 F1 supertube and we're putting on momentum excitations. Everybody knows how to do that. If you're putting down point particles that carry momentum instead of localized strings carrying winding, you should go solve the null geodesic equation in this geometry. Okay, so here's the Lagrangian for a point particle in our BPS background. And if we go take that Lagrangian and we find the corresponding Hamiltonian in terms of the conjugate momenta to the coordinates u, v, and the transverse x, it looks like this. And the BPS condition is, the killing coordinate in this geometry is u. And so the BPS condition is that all the supercharges that square to translations along that killing coordinate are preserved. And so that tells you then that the momentum along the u direction should vanish, is the BPS condition. If you like, it's the energy is equal to the y momentum. minus the y momentum. Um, in our conventions. Okay, so if you set PU equal to 0, you get rid of this term, this term, this term. Okay, and so your Hamiltonian reduces to this thing squared over Z2. But the Hamiltonian is the generator of translations along the world line, local translations, and so the reparameterization invariance condition along the world line is that the Hamiltonian vanishes locally. And so combining the condition of vanishing U momentum and vanishing Hamiltonian, the BPS condition is this. And so it constrains where the the null momentum carrying supergravity particle can live in terms of the quantum numbers you give it. So let's just see how that works for the wave modes that people like to talk about. Well, the wave modes that people like to talk about, what do they look like? There's some, delta LMN is like, sine theta to some power, cosine theta to some power, in some natural coordinates on the transverse space. Uh, R over the square root of R squared plus A squared to some other power, and A over the square root of R squared plus A squared, some other power. Okay, things like this. Okay, and so you have some basis of wave solutions in the round supertube geometry that everybody likes to work with. And those wave functions have peaks. And those peaks have widths that are of order 1 over the square root of L in the geometry. And so they have a peak both in the theta direction and in the R direction. So in some coordinates, which I'm not going to tell you about, R, theta, phi and psi are some kind of Euler angles on some proximate S3. Theta is the polar angle on that S3, and R is the standard radial coordinate. So these are some wave functions that are just like running around in these angular directions, and then sitting at some particular value of R and theta because they're BPS. And the point is that if you go give some particular values to the momenta that the particle is carrying, and you plug in for the value of the harmonic function that is sitting in the constraint that the wave has to obey, then you find the correct location of the wave that you solve for. In other words, the point particle is just the WKB limit of the wave solution. And so as you go to large values of the quantum numbers L, M, and N, the wave localizes on a null geodesic, and you can analyze the properties of the wave by focusing on that sort of center of mass of the wave, which is the null geodesic. Okay. And so the claim is that I've handed you a huge variety of solutions, not in this frame, but in the T-dual frame. And so if we now go to the frame in which I like, which is NS5P supertubes coupling to winding strings, then the locations of those winding strings are just the T-dual of the geodesic equations, which I just wrote down. And so I can just go through the T-duality map and write down directly the location of the string as being constrained by the momentum in the transverse space and its winding along the Y circle. Okay. And so now we've kind of pinned down everything up to maybe some discrete choices of the solutions of this equation. That you write down a generic NS5P supertube, you write down some gas of winding strings that surround it. It's the T-dual of superstrata, and I claim I've enumerated all of them. And furthermore, when these locations of these winding strings is pretty close to the ambient NS5P source, I claim the geometry looks exactly like this. That is, it looks like vacuum extremal BTZ down to the scale where the sources are, and then it resolves itself into a five-brain star carrying momentum and strings. Hmm. Okay, just about done. Okay. If you take the solution that we wrote down and you plug it back into the effective action, you get something kind of interesting, which is what you might call a joint effective action that knows both about the strings and the fibranes, where they talk to each other. So this gets to the discussion that we were having yesterday in Yimin Chen's talk. Um, where you're asking, okay, what happens when you excite this thing away from BPS? Well, you should write down the correct effective action that governs those excitations. And Samir was saying, well, what you see is some kind of effective magnetic field, and you poke the super tube, and it just kind of circles around and comes back. Okay, where is that coming from? That's coming from the fact that the appropriate effective action for the situation I'm describing is one in which um, the strings and fibranes are talking to each other through their mutual separation. But in particular, these harmonic two forms that appeared in the solution act as effective magnetic fluxes. So the string source looks at an effective magnetic flux for the magnetic string of the fibrane, and the fundamental string sees a magnetic field that's sourced by the fibrane. And those effective magnetic fields are then going to um, do the thing that magnetic fields always do. If the string wants to move this way, it's going to send it in an orthogonal direction by a Lorentz force. And so indeed, there is some kind of a trapping phenomenon that goes on where in the presence of the generic wiggly source, this is looking like a random magnetic field. And this sort of term looks like a correction to the moduli space metric. So there's also some kind of random wiggling in the moduli space metric. And so, at the end of the day, all these sources look like if you try to perturb them away from BPS, they're a little bit rigid in the way that Samir was saying, because you try to poke them and they're trapped in the same way a particle in a random potential and a random magnetic field would be trapped. Okay, so okay, I don't regard that as a bad thing. I think part of as the throat gets deeper and deeper, the system um, should be trapping excitations, right? Because that's what, if the thing is starting to approximate a black holes trap excitations for very long periods of time. So this is a good thing. All right. I think I've said all of this, except for one thing. So uh, the the whole thing is supported by the fact that the fibranes strands are kept apart by their self-excitation. So we could ask, is there a failure mode of this system? And the obvious failure mode is you de-excite the fibrane. You de-excite the fibrane strands self-consistently start approaching one another because after all, it's the random walking nature of the fibrane that's keeping it puffed up. So if you take away the fibrane momentum, the random walk gets smaller and the fibranes get closer together. And what did I say? I said that the depth of the throat and the string coupling at the bottom of the throat are all governed by that separation. So if you de-excite the fibranes, the throat gets deeper, the string coupling gets stronger, and you potentially start running into trouble. But now you have the thing that's different between the two charge and the three charge case is that with the third charge here is the string winding, you have an object which you can offload that momentum excitation onto, right? So you can transfer momentum from the fibrane sources to the string sources. And that's actually entropically favorable to do if you have at least one string whose winding around the Y circle is bigger than the fibrane quantum, right? Then the momentum fractionation on that string is stronger than the momentum fractionation on the fibranes. And so there are more modes on the wiggly fundamental string than there are modes on light modes on the fibrane. And so by that sort of, that's one of many possible failure modes of this system where you make the fibrane supertube collapse. And as it collapses, as you offload momentum from it, the the fibrane shrink, the throat gets deeper because the Z2 harmonic function is getting more and more peaked. The string coupling is getting stronger, and the system runs away into the strong coupling region where perturbative string theory breaks down. But so I've sort of sketched that here. Um, but that's okay, right? Stars can collapse. If there's nothing supporting them, stars collapse into black holes. And so I claim this is just some failure mode where this BPS system can collapse towards the black hole phase. What's the black hole phase? It's when the fibranes get close enough to each other that the non-abelian fibrane excitations start becoming light. And that's the black hole phase. The black hole phase is the phase of non-abelian little string theory. Everything that's being described here, which includes all of the superstrata that people have talked about, they're really stars. They're not black holes. And they shouldn't be thought of as being black hole microstates. And we can argue about that. Okay. All right. So, where do you go? You go to some phase of little string theory. I claim that the little strings are describing the black holes. And if there's hope for the fuzzball program, it's that none of this disappears entirely in the effective field theory. You should still have some piece of the effective field theory, which is the five-brane effective action. Instead of saying, oh, all of that collapses into some singularity, you should keep it around. You should just add to it the non-abelian excitations, which you integrated out because they were heavy when the fibranes are on their Coulomb branch. Integrating those things back in gives you the degrees of freedom you need to describe black hole entropy and maintain unitarity in the dynamical evolution of this system, at least in the point of view of effective field theory. All right. So that's my spiel. I think that we should really think of these three-charge solutions that are non-singular and smooth from the point of view of supergravity as being more like stars than black holes. They're not pathological in perturbative string theory as long as you keep the fibranes sufficiently apart. When you don't do that, then you get little string theory and perturbative dynamics breaks down. But you should expect that because black holes are inherently strongly coupled objects. Okay, and with that, let me conclude.
Thanks.
That's very nice. So.
So I have a question, Emil. Why do you say that when you excite the little strings, you get to the black hole phase? Because, for example, you showed that if you look at the supermaze has the little string excited, but it's still locally 16 supercharged. So there's no way on the world you'll get out of something which has 16 supercharges locally anything with a horizon. It's just that something which has 16 supercharges, you can always dualize it to some duality frame where it becomes empty space. And so why would you call the little string phase to be the black hole phase? I would call it the fuzzball phase, which is dual to the typical states of the black hole. But I don't know why would anybody call that the black hole. I mean, why would anybody use the word black hole to describe that phase?
A black hole in the colloquial sense of an object having the Bekenstein-Hawking entropy.
Yes, but
Okay.
the supermaze has the Bekenstein-Hawking entropy, and local
No, I'm sorry.
charges.
I am sorry. You've described a set of solutions which so far are in non-compact space, where you have very coherent supergravity excitations. And a lot of the physics, um, you're you're a long way from describing the physics that I'm describing, right? So you're going to have to figure out how to put multiple of these things into the geometry, which I understand you've done, but then you have to compactify it. The compactification involves all sorts of issues with image charges, et cetera, et cetera. You're a long way from describing the things that are actually involved here. And it's not at all clear to me that your super mazes don't have a strong coupling problem of the sort that I've described. I would be super amazed if it didn't.
Can I ask a question in a slightly different way? When you said these things are stars, I mean, you talked about the fact that there's a long, the black hole phase or black hole situation is very far down the throat. But what's the size of the S1 and the size of the S3 of these things? Is it really, isn't it really very, very close to the horizon area? So from a macroscopic point of view, it looks a lot like a black hole and cracks like a
So
black hole.
yeah, so the I mean you see it in the harmonic function. I didn't write all the harmonic functions just because I didn't want to bore people. But right, the harmonic function looks like this. So it looks exponentially close to the vacuum solution until you get to the star.
Right. So in
But
other words,
this is what you would expect, right? If I wrote down the solution for the sun, it looks like the ignore the solar wind. It looks like the vacuum Schwarzschild solution until I get to the radius of the star. And then it
yeah,
starts differing because there are sources.
but the R5,
Why would this radius be R5? I mean,
isn't this exponentially close to the size of the black hole, or is it actually, it's not 3 kilometers versus 700,000 kilometers like the sun. Isn't it sort of 2m plus a few Planck units?
No, it's governed by this phenomenon. Okay.
Yep.
So remember, I have in the so uh, the depth of the throat is governed by what's the radial scale. How to say this? This is the radial scale I was calling R5. It's where you start resolving the individual sources. Okay. And the dilaton has some value at that scale because it's linear dilaton coming. If I take away the fundamental strings for the moment, okay, the dilaton is growing, and the throat is getting deeper. And so the question is, okay, how close do the fibrins have to come to one another that I'm really, a few Planck lengths away from the extremal, the black hole. What would be the black hole horizon scale? Well, I gave away the answer, right? They need to be a few six-dimensional Planck lengths away.
Okay.
As long as the five brain source is the five brains are separated by enough Planck lengths that you trust the geometry in string theory. I think things are okay. But as you're trying to push things, as you're trying to make, and you guys know this, right? So,
Oh,
the solutions you guys can, construct, the thing that's doing all of this is the angular momentum that's carried by the underlying supertube. And
right.
as you shrink that angular momentum, the source becomes more compact and you get a deeper throat and, you're off to the
But there's no
races.
cutoff. When you have superstrata, for example, the
Wait,
size of this thing is 1 over n1 and 5. It's not alpha prime. It's not controlled by the string length. So the equivalent of your R5 when you have superstrata is actually 1 over n1 and 5.
Yeah, and I'm
So it's
claiming
actually
that
much,
that
much
when
smaller
you
than
when you
whatever
get
we
to
do.
that scale, the supergravity is out of control.
No, it's not. For superstrata, it's not. The deeper superstrata, the supergravity is not out of control. For the deeper superstrata, again, the 3-point functions of which were matched exactly to the CFT. So there's a one-to-one map between the 3-point functions computed on the deeper superstrata and the ones in the CFT. They were matched by Stefano and Rodolfo and collaborators. So those are perfect supergravity solutions.
Something that nobody has calculated in those solutions are what are the quantum fluctuations, right?
right.
Here in the papers that Yoav and I wrote a couple of years ago, we estimated the scale of the quantum fluctuations. The quantum fluctuations of the five brain supertube that's undergirding all of this are of order six-dimensional Planck scale. So if you want to get the throat deep enough so that the fibranes are within a few Planck lengths of one another, the quantum fluctuations of that geometry are becoming out of control.
But the supergravity, so, but the whole point is that there are no more.
Yes, the supergravity solution looks nice and smooth, but I claim that the bottom of the throat is oscillating up and down like crazy. This is the Schwartzian mode.
But there are no
The
more
Schwartzian
fibrates.
mode is
There are
starting
no
to
more.
develop, and it's
Joseph,
governing the fluctuations of the depth of the throat. And once
it's
the
the
whole
same.
point is that the Schwartzian mode controls the whether the geometry is classically trustable. And if you're looking at BPS solutions, you get close enough to the stretched horizon scale. And the claim is that you can't ignore the quantum fluctuations because they dominate.
As if it's the same issue we had 15, 20 years ago when you
Yep.
talked about what's what one Planck length or one Planck phase volume, and
Yep.
it's makes a huge difference. But can I follow up on the question I was asking? You have multiple scaling regimes in your solution. The one thing one thing that happens in microstate geometries is that once you get into the scaling regime where you have a BTZ-like behavior, that sphere around it has stabilized pretty much the horizon scale within epsilon. And so I would argue the minute you're in that kind of scaling regime, aren't you really looking at something which is an ultra compact object, just which is basically horizon scale?
Uh, no, there is a separation of scales, which is basic in my duality frame. It's governed by the depth of the throat.
Okay,
Um,
that's kind of the same as what happens in a cap cap BTZ. There is a
yep,
separation of scales, and as Joseph
there's a
said,
separation of scales. So in the solutions that know and love, there's a scale B, which is where the ADS2 region starts, and there's a scale A, which is the beginning of the cap. And and so I've just replaced those scales by some, you know,
RNS5. Yeah.
yeah, some RMS momentum excitation value, which is playing the same role.
But that's assuming single brains. In our solutions, the brains are dissolved. They are blown up. There are no NS5s there anymore. They're just some supergravity fluxes.
Yeah, though they
No more
reappear. So
NS5s.
in my frame, so if you S dualize to NS fluxes and you T dualize, your KK monopoles that are
But I
making
cannot
this
T-dualize because I cannot
become
T-dualize.
NS fibranes.
I cannot T-dualize. That's the problem. I cannot T-dualize because the solution depends explicitly on Y. All the superstrata depend on Y, so you cannot
Yeah,
T-dualize.
that's not the fault of string theory that you can't do that.
No, but again, if I'm in type 2B, again using NS5 PK in NS5 PKM if I want to get any of the long superstrata, there are no more NS5s. I just have some bubbles which have 1 kilometer size, which are wrapped by 1 unit of NS5. There's no sense in which there are any more NS5s there. I just have some topology and bubbles. So you cannot argue that there's any strong quantum effect when my NS5s are gone and I just have some supergravity bubbles of 1 kilometer size. There's nothing quantum there. But there's a length of the throat issue, which is indeed has to do with angular momentum and so on. But that's a different that's an orthogonal issue. But in terms of like arguing that there's going to be
Oh, Joseph is frozen.
Uh-oh.
All right, who's that?
What,
Joseph,
what
you're
am I
frozen.
getting quiet?
I can
a
get a
strong
word in
coupling effect
edgeways.
of the
Okay.
type you have here, I don't think anything of in the superstrata.
Yes, I think Emil's saying something we kind of knew 15 years ago, which is that, the quantization of angular momentum can cause the depth of the throat and the superstrata to vary wildly. And so it's the same issue. There are
But the numbers, there's some numbers.
quantum fluctuations. Yes, the supergravity is good. It's a perfectly, all curvature scales are small, but the quantization of that geometry can create huge changes of depth. Is
Yes,
that
but the problem
what
is
you're
what
saying?
at which scale?
First, Joseph, is that what you're saying, Emil?
Yeah. So as I say, strength, I've got enough experience with this NS5 frame now that I pretty much understand what's going on. And in particular, we have, solutions where we have exact, worldsheet string theory solutions for supertubes. And the world sheet doesn't give a damn whether you're talking about the NS5F1 frame or the NS5P frame because the world sheet, T-duality is just totally transparent. So if you're making some claim about some geometry, it's smooth because it's some KK monopole structure. Well, okay, the world sheet knows that on some T-dual circle, there's a fibrane source, and it knows whether or not those fibrane sources are close to one another or not. And and there are things like this all the time
But that's ignoring back
where
reactions. There
where
are
where
no,
there's something which you thought was, for instance, a benign orbifold singularity. But as you dial some B field flux and you turn it off, all of a sudden the string theory becomes singular. And we understand what that is in string theory. It's some new throat and some dual variables that's opening up and reaching some strong coupling singularity. So you can't just look at the geometry and say, oh, it's smooth or it's smooth up to some orbifold singularities. I understand. There are phenomena that occur. For instance, turning off fluxes on those orbifold singularities
no, no,
can
no, but
lead to
he will just have, I
solid.
mean, don't put any orbifolds, just keep killing D6 branes. So I have a multi-center solution with some D6 branes or something. Indeed, there are quantum effects. I agree with you. Then Jan de Boer had some arguments and so on. But these quantum effects are controlled by some number, which is large enough over n1 and 5. They're parametrically scaling down in n1 and 5. So you expect quantum fluctuations to hit you when J is over the 1, or otherwise when the mass gap of the throat is over the 1 over n1 and 5. But Emil, I think if I understand correctly, you want these quantum fluctuations to hit at a scale which is way, way, way larger. So in our case, A over B is 1 over n1 and 5. That's sorry, A squared over B squared. That's the deepest superstratum you can get. That has J equals to 1. That's the deep inside the ADS regime. What you want these quantum effects coming from the NS fibrils to hit me when I am parametrically higher than that. And I don't think that
No,
happens in the
no, no,
two-charge
no,
case.
no, no. The
Okay.
black hole phase is always the stretched horizon scale.
But okay, but when you have an ADS2 throat, the stretch horizon scale is you cannot define that. You have to give me a depth. So there's a depth of the ADS2 throat. Of course, all the way from A equal over the B to A over the 1 over and 1 over n1 and 5 times B. So I have a huge range of A's and I have exactly the same size of the S2. So you can say that the stretch horizon is always an S2. That's not a good variable when you have an extremal solution. When you have an
No,
extremal
the
solution, you
angular
can,
spheres are irrelevant here. The
yes,
angular spheres are always size for me root n5. Well,
yes,
sorry,
indeed.
once I start diving inside the cloud, it starts shrinking below root n5 just because my Gaussian sphere
Sure, that
surrounds
of
less
course the
fibrate
same
charge.
is.
Whatever.
But the question is, where do these quantum effects strike? And in particular, I can ask it in two ways. Way number one, I have a base space of my solution. I have some R4 where I put some -5 sources and so on.
So there's a
And on
tension.
that
There's
base space,
the five brane has a natural scale of its tension, which is the six-dimensional Planck scale. And it kind of naturally finds its location in the depth of the throat where it's becoming light enough that you start seeing its quantum fluctuations. So there's an alpha prime. What I'm trying to say is there's an alpha prime of the magnetic string. So you should always keep in mind that there's some scale of quantum fluctuations, transverse quantum fluctuations of this magnetic five-brane string. And if the five-brane centers are becoming close enough that they're becoming, close to that alpha prime scale, then you can't ignore the fact that stretching between those things are some, light non-abelian excitations. And so that scale is always going to be related to the appropriate Planck scale in the supergravity simply because the five-brane's natural scale of wiggling is that Planck scale. And so what you should really be paying attention to is not whether things look, like nice and big and puffy. They look nice and big and puffy because you've multiplied something that's just naturally Planck scale by some harmonic function, inverse of some harmonic function. No, sorry, by some
yes,
pole and some
it is.
harmonic function, which sort of like blows it up to so that it looks, in quotes, macroscopic.
But why that? What
But
do you
that's
mean
a
by looks
fake. That's a
microscopic?
fake
It's big. I mean,
because
I can.
what you've done is you've replaced fluctuations. What do these harmonic functions do? They say, okay, fluctuations of things, locations of things in the transverse space translate into fluctuations of the peaks of the harmonic functions, and the peaks of the harmonic functions govern the depth of the throat. So once you have some large relative strength of fluctuations of the transverse positions of the NS5P source, you start getting large fluctuations in the depth of the throat.
Yes, but those
I, I,
fluctuations
I
peak. I
fully think
fully
that
agree with
that's
you. I
so I
fully
think
agree with
that's
you. This
some
happens.
partner coming from the
But the
non-black hole
question,
size,
sure.
non-black hole phase. It's some partner of the large fluctuations in the Schwarzian that one sees when one tries to approach extremality from the non-extremal
But let's be
black hole.
precise on the numbers. So the point is on the base in the D1E5 system, for example, I can ask what's the size of the super tube which has the deepest possible throat? And the answer is, if you compute R squared with the supertube, so there's an NS5F1 supertube, for example, on which you build a superstrata. When you put momentum modes, the radius becomes smaller and smaller and smaller. The thing becomes deeper and deeper and deeper. And you can ask, what is the size of this supertube when I have the longest possible throat, the one which has J equals to 1? And the answer is the supertube has R squared, which is equal to, again, it's N1 N5 over K squared, and K is N1 N5, so R squared is equal to 1 over N1 N5. So it's, 1 over N1 N5 in Planck units. That's where quantum effects kick in. And I fully agree, and this is Jan de Boer's quantization as well for bubbling solutions. I fully agree we'll have quantum effects kicking in when the size of the supertube on the base will be of order 1 over N1 N5 times whatever L Planck in the 4D base space. Now, what I understood from your calculation is that the size is going to be of order 1 and not 1 over n. And that's the thing which I don't understand. Because this, I want to see the 1 over n 5. If you tell me there's a fluctuation when the size on the base is 1 over n1 and 5, and the throat is, 1 over n is of length n1 and 5, the mass cap is 1 over n1 and 5, no problem. I'm very happy you have fluctuations there. But if I make it a factor of 20 higher, I shut down these fluctuations. In Jan de Boer's calculation, if you make the throat a factor of 20 higher, you shut down these fluctuations. These fluctuations are not there anymore. If you do quantization a la de Boer
Yes,
Samach,
I
you
totally
have
agree.
states
Right?
living there.
When a star is at 10, when the radius of a star is 10 times the Schwarzschild radius, then
We're not
yes, you
talking
can treat
about
it as a
10, we're
star.
talking about 1 over n1 and 5. So when you have two NS5 branes, and you have the picture on the left when the NS5s become unhappy and you have the smooth cap, this transition from the left to the right picture with the X and without the X happens when the distance between the NS5 is of order L string. It's not happening when the distance is of order 1 over n1 and 5. The scale which the scale over quantum fluctuations is much, much higher than what I get in the D1D5 system. And whatever Jan de Boer tells me for
we
quantization.
did all the scalings very carefully. So I don't think there's a mistake in what I'm saying.
No, but the question is, what's the scale in the D1D5 language or in the F1NS5 language, in the supertube language? What's the gap? What's the mass gap, for example, of this configuration at the point where these quantum effects become strong? If you just
Mass gap is governed by the depth of the throat.
yes, but how much is it when the depth of the throat becomes unhappy
Can I just add
in
something?
your language?
Can I add, if suppose you go to a depth of the throat that's 10 times n1 or 100 times 1 over n1 n5.
Mm-hmm.
The radius of the usual superstratum geometry, the radius of the star, is a very tiny amount more than the radius of the corresponding black hole. So there are these two scales, one of which is how far down the throat
Are we talking
about
the size of angular scales or the radial scale?
There's a sphere around the thing, and the spheres are stabilized in size as you descend the throat.
Yeah, everything in the ADS2 region, the sphere is stabilized, the
absolutely,
is
and
everybody's stabilized.
So you keep jumping to, or when it's 10 times the size of the black hole, then a star is a star. Yes, absolutely, but that's not what's happening here. There is a scaling throat where the spheres stabilize just epsilon above the size of the black hole. They are ultra compact. They're not fat stars like neutron stars.
So yeah, so the question is, what is the radial scale of things? Okay.
Well, what's the surface area of the
so the claim is that
what's the surface area of the star, and how different?
So when I say 10 times the Schwarzschild rate, what I really mean is there's some scale. Let's ignore the fact. Let's put aside the fact that yes, classically, the extremal black hole has a horizon which is infinitely far away. Blah 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 blah.
Yeah, right.
We all understand now there's some effective scale, which is the scale of the stretched horizon, okay, which is like a Planck length away from, okay.
Right.
Planck length in what unit? Planck length for the infalling observer, Planck length.
So there's some stretched horizon scale. When I say the radius, which is big, what I mean is relative to that stretched horizon scale. Okay. So when I call it a star, I'm saying that where the ingredients are living is some scale which is sufficiently above that stretched horizon scale that I can treat everything semi-classically. And as the fibranes become closer and closer together, the cap in the geometry gets closer and closer in depth to that stretched horizon scale. Eventually, once you're getting close enough to that stretched horizon scale, you can no longer
Absolutely.
ignore quantum fluctuations in the geometry.
But the question is, what's the number? What's the number in your calculation? Because in the D1, D5, people have done the quantization in the bubbling solutions and so on, and there the number is 1 over N1 and 5 times the in R4 units. So the NS5s in your language, so the would be quote unquote RNS5, the one which you have coming in and helping your solution. If you
It's
look at the
it's
microstate
it's
geometry, would not
it's
be
all
over
the
the
same.
one. It's over
It's
the
all the
1 over
same.
9 and 5.
It's all the same. So
Okay,
if
It's I don't see the N5.
it's nothing that wasn't said 20 years ago, right? It's
Right.
I'm just putting
But
some.
why, again,
Joseph,
keep saying, why would you call
Joseph,
this a star? The surface area is the same as
Joseph,
the
stop a
black
second.
hole.
I don't think he's disagreeing with anything we've been saying. It's just that he's saying, hey, look, this NS5 picture gives you a way of treating the quantum fluctuations, putting flesh on what we knew was going to happen, which is that quantum fluctuations get important when you're very, very close to the mass cap.
That would be ecstatic. I just don't see that.
I
I'm
think
sorry.
that's what he's saying, isn't it?
I fully, I mean, if
Okay,
this happened,
Joseph,
I would be
Joseph, let him
ecstatic. I'd be
stop a
jumping
second
up
and
and down.
let Emil say either he's saying that or he's not.
Yeah, I think so. So one of the results from one of the second paper we wrote, we studied the NS5P ensemble, and we
Mhm.
asked the question, at what scale do the quantum fluctuations of this NS5P supertube become appreciable by studying the two-point function of the harmonic functions?
Mhm.
And the answer is when you get to within a few Planck lengths of the center of mass of the five-brain source.
Right.
In Planck length on the base or Planck length in the full geometry? In the
Six
backreacted Planck
dimensional,
length
six
or
dimensional Planck lengths, which is the natural scale of this magnetic string,
Right.
right? It's it's
yes.
it's it's totally idiotic, right? So the five-brain string has an alpha prime, which is just,
Mm.
because it's a heavy thing, that alpha prime is the six-dimensional Planck scale. So just as you would say an ordinary fundamental string is fuzzy on the scale alpha prime. Okay, there's some alpha prime twiddle, which is the magnetic alpha prime of the magnetic string.
Mhm.
Okay, and that's the six-dimensional Planck length. And so you shouldn't think that you can localize the five brain to better than that scale.
Mhm.
And furthermore, when you start trying to probe or make things that are smaller, as small as that scale, you can't ignore quantum fluctuations. But this is something you've known for,
Yes.
decades,
I don't,
right?
But
I,
That
I
when the
think
depth of the throat becomes big, the quantum fluctuations become large. And all
indeed,
I'm
but
saying is the depth of the throat is related to the separations of things.
I agree with the point. I mean, it's just that, the side is like, people who do vaccine side effects, of course you have, there's a chance, but the question is what dose do they happen at? So, I fully agree that, if you eat aluminum, it will hit you, but, what's the dose of aluminum in the vaccine as opposed to the dose which is going to kill you? So what we're arguing is that, at least in my papers with Nick and also in the Jan de Boer quantization, is that the size on the base space, so again, if you write the supergravity solution, take the NS fibrin, take the fons, take the P, put them all together in some distance. When you have a bubbling solution, it's only when the size on the base space is over the 1 over N1 times N5 that you'll have these quantum fluctuations hitting you. And before that, so even if the NS5 source is officially, they're on some supertube, and the supertube is of size L Planck, there's no way on the planet this is going to be a very happy solution. It's only when the distance becomes way sub-Planckian in the units of, again, of the R4 base,
No, not
that anything
subplancian,
like,
Planckian.
sorry, no, way sub-Planckian, 1 over N1 N5, that's the whole point. Take a
But
supertube.
you have to.
If you look at a supertube of radius r, the r squared is equal to n1 and 5 over k squared, which we can also write as j over k. So when you have a supertube which has angular momentum 1 and which is the deepest superstratum, then the size of the supertube, that would be r on the base of the supertube, is r squared equals 1 over n1 and 5. And that's the place where indeed quantum fluctuations hit you, and that's when the gap is equal to the CFT gap, 1 over n1 and 5, and that's exactly the length which Jan de Boer also gets. So Jan de Boer goes the same length by doing quantization. If you tell me that you're at a scale which is L Planck times 1, or even 1 over n1 and 5 times L Planck times 100, at that scale, Jan de Boer is telling you there are 100 units of phase space. I can definitely live there. There's no quantization problem. I'll be very happy there. So the only thing I'm
Yeah,
saying
and
is
all
the factor
I'm
of
telling you is what
105.
you're describing is a star that is at 10 times its Schwarzschild radius.
It's not the S2 is the same size, so this is the
No,
same.
no, 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 no. Radius, not size of angular spheres. Radial location of the cap relative to the stretched horizon it's the same thing, right? So only when things get down to that scale, the stretched horizon scale, you stop
Okay,
trusting
so maybe
geometry.
then what I don't agree
If
with
the
is how do you
cap
get the
is
stretch?
10 or 100 times further away in radius than the stretched horizon
Wait.
scale,
Okay.
then you have a nice cap geometry, but you also have a star, not a black hole.
So, Emil, I think there's a confusion here being created by in GR. We know that the radial scale is kind of a rubbish coordinate because it covers a multitude of sins. You can only talk about physics of the thing in terms of redshifts, or you can talk about things, or you can talk about the physical
In
size.
falling time.
You talk about the surface area of the star. You can radial coordinates literally mean, well, nothing. Try and talk about the volume of the interior of a black hole, for example. And, this is the kind of reason why radius is a rubbish coordinate. So redshifts are the only thing that makes sense.
In proper times.
And
Proper time from infalling
okay,
observer.
no. Let's not go proper time because that depends on the observer. So what matters is a redshift or a physical horizon area. And so when you say 10 times the radius, I think of something 10 times the size. It's not the surface area of the star is not 10 times the surface area. It's not the difference between a neutron star and a black hole.
And
It's
moreover, if you look at an infalling observer,
okay,
the
okay.
time it takes for the infalling observer to go from the scale to the
Joseph,
horizon is
can I
actually
get an
1 over
answer to my
n.
question before you start? Emil, can you respond to that? You say yes, 10 times the size. It's not 10 times the size. It's I mean,
It's
if you measure the surface area.
I'm maybe abusing language a bit, but so there's some quantity that governs these solutions, which is, what is this wiggly profile of the magnetic string?
Good.
Okay. That's some concrete thing. It's, wandering around. Okay. And it's got some size, which I'm calling R5.
Right.
And depending on what that R5 is, I get some harmonic function,
Mm-hmm.
which has a peak at 1 over R5 squared.
I,
So there's some flat space intuition about how far these things are apart from one another, basically because my base space is R4. And so there's some, coordinates in R4 that I've set up in terms of which
fine.
I'm writing the solution. And
But let's
when I get to that scale, I get
can
to
we
the
measure
scale
it?
where the throat caps off.
Fine, I'm happy, but can you tell me in what that means in terms of the surface area of the
So when I'm
object
talking
you've
about the
created?
size of the star, I'm talking about this R5.
Fair enough, I know, but I'm trying to turn that. I think that the concern that Joseph has and what I have is essentially what does that translate to in terms of the redshift? What is the redshift where things get into trouble, or what is the physical surface area of the star when things get into trouble? A thing that's 10 times the size of a black hole is a somewhat large neutron. Well, it's not even that. It's 30. Yeah, it's neutron star.
Yeah.
It's
So
Whereas I
yeah,
think you're still talking about what I would call an ultra compact object.
so yes, it's true that in solutions which don't have ADS throats, that uh, angular spheres grow with radius, and so that leads to its own set of intuitions about what is the size of the star.
Right.
Okay. Right? Because as the radius of the star gets bigger, the angular sphere gets bigger. Okay, fine. So now we're down in some ADS2 throat, and no angular sphere has a proper size, which is changing as you go up and down. Everything is just,
Right.
fixed size. But there's still a question of where radially things are. Okay. And I claim that I can translate where things are in terms of these profile functions, f of v, what is the mean square extent of that f of v? Okay, that's some R5 in some standard flat space intuition about
Yes.
wandering
This is
strings.
good, but
And
okay.
that translates into where things are in terms of depth in
Of
an
course.
Happy, but depth, when you talk about really is a code word for redshift. So I'll put another way.
It's proper length in the radial direction. Redshift is governed by the TT components of the metric. Those are governed by other harmonic functions, including Z1.
But the proper length as you fall into a black hole is infinite. So you
Not when you've capped the geometry.
Indeed, but then
But if you want to
Joseph,
compare with the black
the
hole, what do you
discussion we're
compare?
having is about when you cap the geometry, there is so as you cap the geometry, there is a cap where you get into danger of quantum fluctuations. At what redshift is that?
At what redshift is that? It's the stretched horizon scale.
Okay, so
So
we're talking
whatever the
plane length
redshift is to the
difference, plane
stretched
length
horizon of
difference.
a BTZ
But
black
is it
hole.
R5? Is it R5 in this language, or what I see in this language is there's an R5, for example, in the formula below, in the blue formula.
Yeah.
Is that the radius?
I don't know.
Because I mean, at that radius, nothing bad can happen. I mean, this is the radius when you want these NS5 brains to start talking to each other and conspiring and smoothing my throat through quantum effects and so on. At that radius in supergravity, nothing should happen. The solution should look like the black hole, quark like the black hole. You are way, way, way above the place where any quantum fluctuation should happen. In this language, the quantum fluctuation should happen when R5 is actually 1 over N5N1 or N5NP or
Yeah, yeah,
whatever.
yeah. So there's a further scaling here which I um, um,
Oh,
haven't
LP6, LP6. You're
specified.
saying that there's
Just
another.
give me a second. So this is in some set of coordinates which is adapted to asymptotically flat space. So in these coordinates, I have not yet taken the decoupling limit. So what is the decoupling limit? The decoupling limit is this R goes to 0, and then there's some, let me call this R flat, okay? G string goes to 0, and then there's some R which is equal to R flat over G string, which is being held fixed. That's the NS5 brane decoupling limit.
Mhm.
When you do that, okay, so this is R5 flat, the sort of natural asymptotically flat scaling of coordinates where things look like random walks. When you do the scaling, the G string in the cap gets factors of N1 and N5. And so in terms of this R, which is the relevant R for the five brain throat, the R picks up some factor of, maybe Yoav can help me out here. It's like 1 over N 1 N5 to the 1/4, I think, something like that.
Oh,
Yes, that's in the two charge case.
That's in the two charge case. So yes, right. The things are getting very, very close together. And from the point of view of somebody who's living out in asymptotically flat spacetime, from the point of view of somebody who's just sitting in some scaling five brain throat, um, uh, uh, yeah, things are extremely close together.
because in the supertube case, I cannot write on your on the Zoom, but on the supertube case, it's really that R squared on the base. Again, this R squared is actually 1 over N1 and 5. So it's actually much, much smaller, the place where quantum fluctuations and garbage starts happening. In the superstratum case. So again, if you take, I mean, again, simplest example, um, take our superstratum and, just look at the solution which has J equals to 1. So the strands which has, the lowest mass gap possible. So A over B is 1 over N1 and 5. If you look at the would-be radius in the R4 coordinates, so again, the brain, in the R4 where the brains are, the radius of that object would be actually 1 over, it's going to be R squared is equal to 1 over N1 and 5.
Yeah, you have to choose. You have
The
you have to be
power
you
here,
have
which
to
is
be
2.
smart about what's the scale. You have to be mindful of various rescalings that you do to take the decoupling limit. Okay.
Mhm.
And so there's some natural set of conventions for how do you rescale the coordinates to take the decoupling limit, where the R, for instance, is the natural global coordinate in ADS3, um, and or for BTZ. Okay, and so we work in those coordinates, and yeah, so there, yes, you know, there's a whole version of everything written here that's working in some scale coordinates where you just, you're actually working in the decoupled theory, which is, asymptotically linear dilaton, et cetera, or asymptotically ADS3, which is trivial modification. So yeah, all of that can be done. and has been done. And I'm still telling you that um, all of the superstrata where you have a nice cap geometry and it's semi-classical all the way, they're all at. I'm not telling you anything you don't know, right? All of these
No, no,
solutions,
don't let me
they
confuse
cap
you.
off at a depth which is such that you trust the classical geometry.
Right.
But as a consequence, the underlying five brane that's sourcing that five brane supertube is puffed out uh, well beyond the scale at which the non-abelian excitations, which govern the black hole phase, could possibly be excited. So I'm not saying anything that should surprise you. I'm saying that a black hole phase transition is a it's Gibbons-Hawking on the gravity side, but it's a deconfinement transition on the gauge theory side. And the natural non-abelian excitations here are this little string sitting inside the five brane. And so until you can access those excitations, you don't have a hope of capturing the black hole entropy.
No,
But
I know this we know.
okay. But when do you start accessing those excitations? When the quantum fluctuations of the five branes start becoming important.
Can I try to take the conversation slightly different direction? I mean, the question I've always had in the back of my mind over the years is to what extent the supergravity is useful. And so, once again, we're back at this point. There's a perfectly good supergravity solution, but we know quantum fluctuations wipe out things on scales of kilometers or megaparsecs. So, but I've often thought that what that really is signaling is when you have the three charge solution, the geometry gets blown out and puffed out because of the harmonic functions, and you seem to have good control of the supergravity. Is it that supergravity is still giving you good collective coordinates to
So
the
it's
strong
true that all of the angular spheres and
yeah.
circles are getting puffed up to ginormous values because that's controlled by the charge quanta, and the charge quanta are enormous.
I
Absolutely. What the one thing that remains is, are there quantum fluctuations in the geometry radially?
no,
And can you control them?
I want to take that. Okay, I want to.
And you guys made this point again like 20 years
No, no,
ago.
no. I want to make the point I want to ask is do you still think there's a use for the supergravity solution in this strongly quantum regime in the sense of, yes, there are lots and lots of quantum fluctuations, but the supergravity moduli are in some sense the sort of zeroth order things that you should semi-classically quantize in order to understand the effective geometry that you're making.
So I think the way I would answer that question is that supergravity should be valid. So my sort of picture of what's going on is that, okay, if you want to access the black hole phase, you really have to let the five branes become non-abelian. And then you should integrate in the little string excitations that are there.
Mhm.
And then you get back to this long string picture that we've had since Strominger-Vafa, right? The little string is the long string living inside the five brane. It's just that all of that is now taking place down some long ADS2 throat and some effective field theory. It's not some, weakly coupled symmetric product crap. It's actually part of the supergravity, and you should take it seriously. And so it's that little string that is then coupling to the bulk ADS2 throat. The bulk ADS2 throat, I think you should be able to treat with by semi-classical supergravity within a few, Planck lengths of the stretched horizon.
Right.
But the question is how well can you capture the dynamics of the stuff below that scale, which is the stuff that's capturing all of the black hole microstates
But
and
suppose
how
I
it interacts with the bulk.
But the gap you're getting out
suppose
of
I
this
make a solution which has got many, many fractionated branes, 100 branes in each pile so that supergravity applies. I can presumably make a fairly good semi-classical description of that space. It is not the phase you're talking about, but it's still giving you some semi-classical picture of that phase.
Yeah, it's there are things, there are stars, there are galaxies, there are all kinds of things that you might want to describe in gravity.
No,
They're
but
just
those are not
No,
galaxies.
that's
And,
disingenuous. No,
when
that's
you have the
bullshit
sun and I fall
answer.
into the sun, the time it takes me to,
Hold on.
if I have a black
Can I,
hole with a sun mass,
can I follow up,
a
please?
proper observer takes a
Can I
huge
follow
amount
up?
of time from the
Yeah,
moment of the radius of the sun to the black hole horizon.
yeah,
If
Joseph,
I look at these geometries and I look at the black hole and I look at at an infalling observer, the time it takes me from the moment I hit the structure to the time I would hit the horizon is 1 over n on n5. So those are from the point of view of the infalling observer, all these objects are really sub-Planckian above the horizon. From the point of view of the infalling observer, you have to look at the right radius. You have to look at the right coordinates. So again, if you take an infalling observer at the black hole and you take one at the sun, and you say, let's take the black hole with the mass of the sun and let's see how much time it takes the infalling observer from the place where the sun is to the place where the black hole horizon is. You'll get the number over the minutes, or like, seconds. But if you have it in our microstate geometries and you take the black hole solution, classical solution, and you take the solutions, the time the infalling observer takes to go from the place where the structure is to the horizon is 1 over n(1n)5. It's
Nobody's arguing that there isn't a
So why do you
long
call those things
Joseph,
stars?
Joseph,
Why do you call those things stars?
Joseph,
A black hole plus 1 over n(1n)5.
Joseph, can I follow up on my question? Answering this, if I start talking about coherent microstructures that I find at the bottom of a long throat, it's very disingenuous to say, oh yes, well you might be able to describe galaxies and stars and other things in gravity. That's a disingenuous answer. I'm saying that there are probably coherent structures that you can build by fractionating branes in coherent ways at the bottom of the throat that give you a semi-classical picture of what the microstructure is that you're describing. So an answer that framed in terms of describing galaxies and dark matter is a bullshit answer. So do you have a better answer?
Look.
Question to me or to Emil?
So, just let him answer, please.
So I think the question we should all be after is, what are the degrees of freedom that are not being captured by those solutions, which are necessary for describing black holes? And I claim that that you're off in some other part of the phase space, and you can explore that phase space, and it's got lots of interesting structure, lots of interesting solutions, and there's plenty of work to do. Okay, but are you capturing, the original hope in this whole microstate geometry, looking for bubbling solutions, constructing superstrata, et cetera, was you say, okay, maybe I'm not capturing all of the entropy that is there in the BTZ black hole, but maybe I'm sampling the phase space in a generic way. And so the things I am constructing, are a representative sample of black hole microstates. And I'm claiming that, no, you're off in some other part of the phase space where you've suppressed all the non-abelian excitations, which are the things that actually are responsible for the bulk of the black hole entropy. And so when you're not sampling those, you're not learning about black holes. Simple as that.
But I think there's a problem with the phase space. So the problem is when you have a quantum system, the quantum system spills from the Higgs branch to the Coulomb branch. So here, even if we are not looking at the non-abelian excitations, which give you torus modes, you still get the mass gap, which is the correct one for the long string. When you have the longest possible superstratum, the mass gap is exactly 2 over n(1n)5, which is exactly the CFT perturbative mass gap. And that's the one which people also get by looking at the Schwarzschild mode and so on. So the mass gap you get correctly. So clearly this solution, even if supergravity doesn't resolve for you the torus, it resolves the fact that some of this wave function has spread onto the sector where the black hole entropy is, and you have a mass gap which is over the 1 over n(1n)5.
Nobody says that
you cannot get the 1 over n(1n)5.
Look, there are some things that that will look like things in black hole physics, right? So there might be excitations that have large redshifts that are trapped for a very long time, as I was describing before.
No, but I'm
some
talking
kind of
about the CFT
random
mass
magnetic
gap.
field that kind of traps X. So there are things which kind of mimic features of black holes, but this.
But there are things which you
Do I
can only
capture
get
the
from the
generic
sector
phase
you
space?
would.
Do I capture the fast
No, you
scrambling?
don't
Do
capture the
I
generic
capture the
phase.
maximal chaos? No.
Oh, sure, that you do. That I think you'll do. So there's a paper by Arnab and by Shumi Das that the moment you put a brick wall model, you'll always get the maximum chaos if you put it deep enough. That's not. I mean, I don't think that's so much the issue. I think the issue is there's a feature which you can
You get the
only
maximal
capture
chaos
with
when you
this.
can access the black hole entropy.
Sorry.
When you get maximal chaos, in the sense that Yiming was describing yesterday. strong chaos, that's
Mhm.
that's requiring the black hole entropy.
Indeed. No, but I think that
You
the
have to
point you're
be you
making
have
is
to
that
have to be rapidly exploring, this whole business about the Thalys time. It's that you
Mhm.
access relatively rapidly the entire phase space.
Yes.
And you're not doing that with stars. Stars
No, but
have,
when you have a deep
ringing
throat, it
modes
doesn't cost you
that
anything.
take, they're slow because you have a huge redshift, but they're not rapidly exploring the phase space. And that was the whole point of the discussion yesterday.
When you are deep down, I mean, when everything is happening in a shallow solution, indeed, but when everything is happening deep down the throat, it's much easier to explore the phase space because it doesn't cost you any energy. With a tiny amount of energy, I can go all over the place, especially if I don't have angular momentum. But coming back, I think the point I want to make is very simple. You are claiming that we are describing a phase which doesn't capture black hole physics. Now, the phase which does capture black hole physics has a mass gap, which is again 2 over n 1 and 5. We are capturing that. So
That's
nobody can say
because the
that our
throat is long. Yes, the
sorry,
throat is long. Absolutely. I
but
wouldn't disagree with
no,
that.
but the point is that gap, 1/2 and 1/5, only comes from these fractionated modes. It cannot come from deep brains which don't fractionate. So the fact that we are capturing in supergravity the 2/n1/5 mass gap implies that some physics of these microstate geometries is seeing the fact that these NS fibrils have fractionated and they give you these low mass modes. Because if you only have Coulomb branch NS fibrils, or you have these F1p strings and so on and so forth, those would never give you a 1/n1/5 mass gap. There's no place in string theory where you can get a 1/n1/5 mass gap unless you are in the black hole phase. That's I think the point. So from that perspective, I don't think anybody can say that the superstars are not capturing, are capturing a different phase. They have some properties corresponding to a different phase, but they also have some other properties corresponding to the black hole phase. And the point is the wave function is spilling. That's I think the way, I mean, the quick way to understand why.
Yeah, I don't know that intuitions that are arrived at from thinking about the symmetric product orbifold are necessarily, you can just carry them over lock, stock, and barrel to a supergravity regime.
Sure,
I
but
mean,
also people who do JT gravity, they find the same. They also find the mass gap, which is 1/n1/5, 2/n1/5. So people who do, I mean, so it's clear that in the perturbative calculation, the
that's
D1
just a statement
system,
that you have a long throat.
I
That's
don't think
just a
it's
statement
only
that you have a
that,
long. I'm
because
not
again,
I'm not arguing that you don't have a throat whose
no, but
depth is
in
order
super
n1
in
and 5.
non-supersymmetric JT gravity, you don't get a mass gap. The mass gap only appears if you do supersymmetric JT gravity, so it cannot only be the long throat, because if you have the wrong field content, if you have a crappy JT gravity, which is not supersymmetric, you don't get a mass gap. It's only when you do supersymmetric JT gravity, which is the one coming from string theory, that you get the correct mass gap and you get the CFT. So I think it's clear that the perturbatively, if you perturb around the black hole background, you will get this mass gap. That's a feature of all the black hole states, and that feature is captured by these geometries. Now, indeed, I fully agree with you. There are many other features. I fully agree with you that the more generic solution will involve torus modes. Again, I think we understand how we're trying to build a supergravity solution. We don't have it yet, but it doesn't mean that the solutions we have are not capturing this aspect of the black hole phase space. That's the only thing which.
I'll make another related point. I mean, suppose I concede the point that supergravity is going to be very bad at seeing non-abelian degrees of freedom. It's just going to fail. However, if I've got SU, if suppose n is 10 to the 6, if I build a Coulomb branch of SU10 times SU10 times SU10, 10 to the 5 times, I can see that in supergravity just fine. And that should give you some inclinate, and then you can look at the massive strings between the different SU10s, the massive hypermultiplets and so forth. You can see that in supergravity too. And so you should be able to get some information about the phase space of the non-abelian theory by studying things where you've broken it into Coulomb branches for which the supergravity works. And that's what the supermaze is trying to do, amongst other things. And so I don't think it's as bleak as you point out. You say supergravity is never going to see non-abelian stuff.
No,
It,
I'm not saying it's not going to see it. It's going to see it as a heavy excitation on the Coulomb branch.
I think it's going to see it as an excitation on the Coulomb branch, which has a mass, and that mass can be taken to zero in much the same way. My favorite example of this is heterotic type 2 duality. I mean, we can see the heterotic string inside a Calabi-Yau
Yeah, it's
manifold.
a heavy
We have
soliton.
to use the imagination to understand that when the cycles of the Calabi-Yau hit alpha prime, then we see
Mhm.
the heterotic
Right.
string. I think we can do the same for black
Those
holes.
are not Coulomb branch again. I mean, it's very
No, no,
important.
no.
Those
But
are
I
not
think we
Coulomb
do it.
branch. Coulomb branch doesn't have an 105 mass gap. There's no way on any Coulomb branch is
Okay, okay, okay.
get a
Joseph,
1 over
Joseph,
105
I
mass
wanted to
gap.
put that point on one
Those
side.
are Peace
We
branch
can keep
states.
repeating that
Okay.
story, or we can move on and discuss
Okay.
other things. I'm trying to move on to the other thing, which is if you build super mazes, does it give you insight into black hole microstates? And I think the answer is yes. And it's because you're looking at the Coulomb branch with massive excitations. It's like your W brains. The same thing is you can build
Yeah,
the
yeah, yeah, yeah.
massive analog of W
Right,
brains.
so I have my wiggly NS5 brains.
Mhm.
There are, D strings that stretch between them, or D2 brains, depending on which flavor
Yeah.
of type 2 I'm in.
Mhm.
Okay, those are the non-abelian excitations, and indeed those are the things that are becoming light when the five brains get close enough together.
Yes,
So
if I have a
yes, I
million
can
of
see
them,
the non-abelian excitations as string theoretic objects. I'm just saying that again, am I um, am I capturing the part of the phase space, the huge part of the phase space, right? The much
if I
bigger
have a
part of the
million
phase
of
space
them, I
where those
still,
things
what
are
are
Joseph,
they?
light.
stop. Okay.
So
If
so
you put
so
if you put enough of those together and you put momentum excitations on them and see them in
yep.
supergravity, you start sampling the phase space very richly. Whether you get to the magic entropy is unclear. But if you put 10 NS5s or 10 D5s, 10 whatever's in a heap, enough to see the supergravity, and you put 10 of them across, you can make a supergravity coherent solution. You can put momentum waves on it, and you start seeing things which grow, whose entropy grow like N1, N5 times root
I
N1,
don't think you
N5P.
will because they're heavy, right? So you don't have the free energy to excite them freely,
No,
which
no,
you
no.
do in the non-abelian
What do you
phase.
mean?
So
What
you
do
will
you mean?
see them as excitations. I mean, we did these estimates with David and Stefano when we were looking at the NS5, the two charge supertubes where we can explicitly construct D brain states.
Right.
So yes, you can see D brains that are stretching between the NS5 brains. Are they light enough that they're making some appreciable contribution to the entropy? No. So yes, you can see the non-abelian things as heavy excitations on the Coulomb branch.
No, but
When
I'm
they're
not
light
thinking about
enough
those
that
things.
they're as light as the fundamental
I'm
string,
thinking about
then
the
a whole new branch of phase space opens up.
I think, but I'm thinking about the momentum waves, the BPS momentum waves that will travel on that system, and those I think you can see in supergravity, and they'll be BPS.
Yeah, sure.
So you count those, you stand a decent chance of getting an entropy which is of order NS, N1, N5, NP, square root.
Uh, no, not
Every intersection will carry a momentum wave. You can put as much momentum waves on as you like, and there'll be order N1, N5 intersections.
yeah, maybe I spoke too soon when I said it would be BPS. I actually don't think they are.
Okay, I think an individual, every single so here's how we might agree. Every single intersection, you can put an N1, N5, an NP on it. I think that can be made BPS. It's when you start putting multiple intersections into one solution that I think you start lifting. Joseph may disagree with me, but I think it's reasonable to expect that a single intersection loaded with a momentum wave can be made BPS. Multiple intersections, I think they'll start disliking each other. There will be a mass scale, and it's probable that they will be lifted. However, they will still be at very high redshift. If you build them into a solution, they'll be near BPS, and that's how I would hope that you might be able to build the black hole entropy into a supergravity solution. It will not possibly be BPS when it's multi intersection. I'm making him think anyway.
Maybe we should open the floor to other people.
Yeah, we could
Yeah,
indeed.
yeah.
We should shut up.
By the way, I'm in Collège de France. I'll start moving towards. I'll join you on Zoom on the phone, but I'll make you guys co-host and host and so on. And in case there's some, I mean, I need to take the RER to get home, so I make Emil host and I'll make Nick Oh no, sorry. I need to make Nick co-host first, and I'll make Emil host, and then I'll join from the other computer so that from the phone so that I can start slowly walking. Okay. So I'll join from the computer now so that I can have and but you should keep on discussing.
Hi, Emil. I
Hi.
have somehow a kind of picture, and I would like to confront this picture with respect to what you said. Um, uh, I would say that I'm more thinking in terms of the free orbital point, but maybe I mean, sorry, forget about the free orbital point. Think about the D1 D5 system and the original Soomajava idea of saying that the black hole microstates are essentially the long string sector with like the D1s. The open string between the D1 and D5 when the D1 is like maximally winded and the D5 is also maximally winded, so that you have like effective strings of length N1 and 5. So suppose that these are all of the black hole microstates. And that if I consider the system where actually all of the D1s are separate, separate in the sense that they are in the same point, but they are the winding number is essentially like one D1 and then another D1, another D1, and the same for the D5s, right? So I have single winded D5s and single winded D1s of length one each. So on that side, if I can construct if I put momentum on the second thing, then I would expect that I do not get a my black hole microstate, because then when I hit when I put momentum on that, then it could be that well, whatever back reaction I get, then the effect is like too far away from the would-be horizon scale. But what about the states in between? If I decide to split my D5 into two parts, and I keep my D1 into one part, into one single winding, multiply winding D1, what do I get? Am I supposed to get a pure black hole microstate, or am I supposed to get something that is like a black hole that is dressed with some stuff? What's your opinion on this?
Yeah. I'm not sure I can answer your question directly, but I would like to make a point related to what you're asking, which is that the reason why I'm a little bit um, um, hesitant to talk about the symmetric orbifold point is that the symmetric orbifold point is the vicinity of the moduli space of this system where the effective description has a single five brane coupled to end strings, bound to
Right.
end strings. Okay. And so you have a single five brane. Everything in this system has no non-abelian excitations. The little string is the fundamental string. It never fractionates.
But
And,
suppose that I
and
that I go
yep.
back. Suppose that I you dualize myself to the point in moduli space where I am really talking about N1 and fives, sorry, N1 N1s and N5 D5s, and
Then I don't know what language to use in the CFT. The CFT is not a symmetric orbifold at that point in the moduli space.
right. But can I not just take the old story about I mean, just take a heuristic picture, and that it feels like I could have in the phase space of whatever I can have in my ADS three throat. I could have like the pure black hole phase, pure black hole microstates, graviton's phase, and then something in between, like for example, a mix of the two. For example, like black holes dressed with gravitons or something like that. And it's just that for me, I would expect that there should be like some transition between point A to point B. And then the mixed phase could be, to have like different properties. Maybe what you are saying, you're suggesting is that superstrata and whatever we were discussing before are actually describing somehow the mixed point A and point B, somewhere in between. And this would explain why we have the right mass gap.
Yeah,
But
I don't know how to localize things in the throat using the symmetric product description. So one thing that's become clear recently through this work of Gopal Kumar and Gabardine and Eberhard and collaborators is that there is a string theory dual to the symmetric product, where indeed the little string is the fundamental string, and it's like just winding, capital N times around the Y circle. But it has this feature that I've been emphasizing that strings don't live down here. If you look at their calculations of correlation functions and where the path integral is localized, the path integral localizes at the top of the single five-brain throat. Right? They have only a single five-brain. All their correlation functions live at the boundary of their ADS3. And there is no local dynamics in the bulk. And so that's why I mean, it would be nice to have some heuristic picture using that language of where things are localized in the bulk, but the starting point seems to me all wrong. That you can talk about redshifts and so on and strings mixing, and Samir has very nice pictures of how things fall into ADS3 using the symmetric product language. Um, but I agree, it's extremely heuristic, and maybe there's some sense in which one can build a language where one can talk about, having a five brain here and a string there and so on. Um, I, I'm just not sure how useful it is or um, how one would calculate with it. Um, so that's why I kind of started with an effective supergravity and brain effective action, which was relevant for the duality frame in which I'm working and captures all of the low energy physics, um, at least all the low energy BPS physics. And so, I can talk about, okay, I have a five brain here. It has this shape in the transfer space, and so on and so forth. I mean, it's the right description. So it should be capturing all the physics, and I think it does.
okay, thank you. Thank you.
And I just don't know. I don't know how to translate everything I said in this talk to the language of N5 equals 1 and the symmetric product. I don't know where to begin, how to localize things in the throat. And
But what about the point with N1 D1s and N5 D5s? Even that you cannot translate to that language.
for you're referring specifically to the S dual frame of D1s and D5s, or you just talking about yes?
No, but so the CFT the free Oberthur point is like is due to the point where there is N1 and 5 D1s and 1 D5, but I just want to not focus on that point, but focus on the point where I have N1 D1s and N5 D5s, and try to get everything from that picture to see what phase is the pure black hole and what phase is the gravitons and what phase is the mix between whatever
Yeah,
both of it.
I would claim that we have a very limited understanding of the dual CFT, and what understanding we do have really comes from analyzing string theory in the bulk,
Mhm.
and and so all of the non-perturbative physics associated with black holes is we don't really have a language to describe it, at least at the moment, as far as I understand.
Okay, thank you.
Yeah, hi Emil. I have a question about the counting that you showed by Masaki, which is parametrically smaller than the Bekenstein-Hawking.
Yes.
But you are saying that it's not exactly a problem, but rather it's a feature of it's not a bug, but it's rather a feature of these stars, these let's say five brain stars. And if you want to understand the square root of N1, N5, NP, you need to know strongly coupled little string theory. So would you say that, I mean, there is no way of understanding the black hole entropy in this approach? Like this is kind of a dead end now?
Yeah, I think so. Um, uh, so I think I understand this as saying, okay, in the regime in this regime, it's saying, okay, I have some wiggly NS5P, and now I'm going to have some gas of winding strings that surrounds it. And that's what's being counted, right? So we take the usual superstratum frame and T2. I mean, again, in various approximations. So I'm treating the momentum waves as point particles that when I T-dualize them become fundamental strings, and there's a sequence of approximations that's being made there that is the subject of some virtual papers that are in gestation. But assuming all of that is correct, then I think I have given what I would regard as a complete heuristic picture of what is the physics that's captured by superstrata. That it's this gas of stuff, okay? And the gas of stuff is puffed out to a scale which makes it, bigger than, it self-consistently locates itself in a throat whose depth is much bigger than the depth of throat that would be relevant for black hole physics. Um, and so, when one shouldn't necessarily, I mean, maybe one can find some other ways to, decorate this that gets you more entropy. But it's sort of like obvious to me the way to access the bulk of the entropy, which is to make this wiggly thing smaller. And the smaller and smaller I make it, the deeper and deeper the throat is. And precisely at the point where I start accessing the non-abelian physics, which we know from calculations of black five-brane entropy is where the black five-brane entropy and BTZ entropy comes from, is that non-abelian physics.
Yeah,
And
but there
so,
you lose control of all your
but there you
calculations.
lose control over the calculation.
But let me throw in a comment. I don't disagree that superstrata basically run their course in this respect. If you sit in six-dimensional supergravity, we now know that we're limited to this picture with
Yep.
this entropy that Masaki calculated, and we're falling short. And so this is why the whole super maze, the whole sort of can we do better by going exploring, multiple intersecting branes on the compactification manifold. I still think there's a hope of moving that discussion in a direction of getting closer to the entropy. I mean, I remember 20 years ago when the best entropy we could get was going like Q to the quarter or something. And
Right.
if you start the superstratum, I think we have a complete picture of what it does and what it doesn't do.
Yeah.
And part of this non-abelian degrees of freedom that we're talking about involves the extra dimensions and actually looking at what's happening in the intersecting brane pictures. And I don't think that's run out of gas yet. So
No, that really is just starting. And so there's a question of how far one can go with
exactly.
that.
And that's that I think
And
I
and I wouldn't, pull your funding because I've decreed that it's a dead
no,
end.
no, but I think the dead endness, if anything, is really the superstrata story has run its course, and this is a nice elaboration of what it's missing. And we kind of knew from Masaki's calculation that we were running out of gas and we weren't going to get there. And this is telling us pretty much what the picture is in six dimensions. And I don't disagree with that. I think that's exactly where, but this is where the whole transition to super mazes starts becoming important. It may be that semi-classical considerations in more dimensions will give us a better sampling of the phase space. And that I think has got legs on it.
Yeah, I think the question I would ask you to keep in mind
Mhm.
is when you're constructing these solutions, um, how do you suppress the non-abelian physics of the five branes? There are M5 branes in the things you're constructing, and you need to. There will be strong coupling physics that's beyond supergravity, unless you keep the M5 branes abelian. And so the question to keep in mind is what in your construction does that?
I think
Uh,
that's
right now it's that your solutions again have your five brain flutes separated from one another.
Yep.
But can you maintain that when you feed everything into compactifying on T4 and putting and wrapping things together so that you have a bound state and so on and so forth?
I think there's always going to be a bunch of control parameters you have to keep you in a good supergravity regime, just like you did with superstrata. There's a maximal depth that is plausible given the quantum conditions. But just like, again, I've trotted out this analogy many, many times, but people managed to do the ideal gas and get the entropy of an ideal gas from kinetic theory of gases long before they knew the Planck constant. You just have to think about balls of a certain size bouncing around off walls. You don't know how to, you just quantize the phase space, but you don't need to know that detail. And I think supergravity, we started off initially getting Q to the eighth as the thing when we talked about partitions over bubbles, and then we put momentum waves on them. And so by going to more and more dimensions and making more and more exotic supergravity models, we're getting more and more of the phase space. There's no doubt supergravity is an effective theory. It's not string theory. And so, but the question is, how good an effective field theory can it be, and how well can it approach describing the microstructure of black holes? And I think there's a lot more wiggle room in 10 dimensions than there is in six.
That's for sure. I mean, very early on, I said, let's compactify everything on the T4. And well, when the fibranes are non-abelian, all of the interesting physics is on the T4. And yeah, I mean, by all means, let's see how much of that can be captured within supergravity when you go back to first principles and say, let's not ignore the T4 structure and let's think about things that could potentially be localized on the T4 in some interesting way.
Yeah, and
Uh,
I think the point, I think the point about what gets lifted and what doesn't get lifted in that context is going to be even more complicated. But I think, by zooming in on various pieces and simple things, we still don't know, for example, what the role of multi-centered solutions are in 5 dimensions or 6 dimensions. They are obviously some kind of lifted states, but they're still part of some conformal field theory. What they are remains to be seen. And so I think it's going to get even more exotic when you start looking at multi-intersections on the T4 or decompactified R4. So
mhm.
I think there's a lot more to be said in these, but I think to answer Simon's question, the dead end in some sense is that we're done with 6 dimensions. We know what it can do and what it doesn't do through a lot of hard work.
No, that's fine. I mean, that's fine. So, but you brought up the question of multi-center solutions. So, are you sure that these are not part of a long multiplate? I mean, are these a part of the short multiplate?
I think the general argument is they're generically part of the long multiplet, look, talking as a supergravity person, I can put multi-centers to a very high redshift. So even if they're lifted, I can make their energies extremely close to the BPS one. So supergravity, I think, is perfectly capable of making solutions that are essentially very, very close to being BPS, if not BPS. And for me, that's good enough. If I'm sampling the phase space of things that are extremely close to being zero energy, hey, I'm getting at the structure of the black hole. And as Emil will point out, if you're on the Coulomb branch or the Higgs branch, you've got massive stuff. But you can imagine sending the separations of the branes to zero, and you can then get at least some probe on the phase space of the massless theory. Whether you get enough, whether it's complete, remains to be seen. But that there are still open questions as what the whole, even in 5 and 6 dimensions, about what the multi-centered solutions represent. I still don't know after many years. But I think all those issues are going to come back in full force when we start looking at intersecting branes in 10 dimensions.
What in what you're doing, what is the um, value added beyond looking at so in what I described here, I've got some explicit configuration of NS5 branes. Okay.
Mhm.
Now I could decorate it with some Born-Infeld action describing some branes, some D branes that are stretching between the 5 branes.
Right.
Okay. But that, of course, is not a back-reacted solution.
Right.
It's not a full supergravity solution, it's some probe approximation.
Okay.
So what is the value added in this case of studying the full supergravity back reacted on the D branes as opposed to just saying, okay, I've got some D branes stretching between the phi branes?
Okay. So the kind of thing I'd like to know is whether I can. Well, let's start simply. We now have simple examples of intersecting brane solutions with which are kind of supercharges. They're called a BPS. You can zoom in on those, and you can use the solutions but created by Doker and Backus and others to actually see a single intersection. What hasn't been done there is loading those single intersections with momentum waves. Can you build a single intersection with an arbitrary number of momentum waves running along the common intersection? There you go. And then can you build the supergravity? That would be a zoom. That if you can make the supergravity discussion of that, then you'll getting to the point of being able to look at imagining what the space of multi-intersections carrying momentum waves looks like, which is exactly what we're supposed to look at when we count the black hole entropy. So we can do one intersection exactly with a whole bunch of partitions of momentum waves onto it. Hey, I think that would be value added. There's a conformal field theory
Is there
associated
some
with the
phenomenon that I'm supposed to observe that I couldn't have intuited just by thinking about the sort of tinker toy picture of intersecting branes?
Yeah, except I'd like to know what happens when you have strong coupling, you back react. You should always find something new and interesting when you do the back reaction. I mean, you know,
Mm.
if you think about Hanani-Witten stories, when you back react that's a much richer and more complicated sort of holographic field theories. Moreover, if you take the M2, M5 intersection, we know that that's not a simple tinker toy brane. The conformal field theory of that
Right. I mean, the thing you might want to hope is that some of this strong coupling physics that I've been claiming is needed. It sounds like what you're hoping is that some of that strong coupling physics gets geometrized.
yeah. And
And
I guess the question,
I guess what I'm asking is it the right strong coupling physics? Is the strong coupling physics that you need to understand for the black hole? Is that what's the intuition as to why that's being captured by what you're doing?
okay, so what I'm supposed to think about when I try and capture the right amount of entropy for a black hole is I'm supposed to think about the moduli space of multiple intersecting branes, or moduli space of D1s inside D5s. There's some moduli space which I'm supposed to then decorate with momentum. And so if I'm looking at in some phase of the black hole phase, if I can actually find BPS states that correspond to partitioning momentum amongst multi-intersections, if I can build a fully back-reacted version of at least one intersection, maybe I'll discover something new about it, but at least I will have got a conformal field theory sitting at that intersection, and I'll be describing coherent momentum modes within that single intersection.
Can
Perhaps.
you see yet if I one thing that kind of worries me is that you want to take the T4 and you want to decorate it with a number of intersections that's growing parametrically with the number of branes. And
Yes.
so are you going to be able to keep
Keep
the
them far enough
branes
apart.
separated far enough apart that you can trust the supergravity solution and avoid
It depends.
non-abelian physics?
I certainly, if you certainly won't be able to get them far enough apart if you go down to one brane. But I there's a parametric problem, which is there's going to be a maximum number of branes you can load on or maximum number of intersections C before
If
you.
you put them in chunks of 10, I think you'll get a sphere around every bunch of 10 fibers, which is going to have a size of 10 Planck. So even if they are at very tiny distance away from each other, if you just put them in chunks of 10 and 10 and 10, they'll blow up the space transverse to them into spheres over the 10 L Planck. So you'll get a solution. That much is clear.
It's the question about it's similar to the question about you know, if I go on the Coulomb branch of SU 10 to the 6 Yang Mills, where do I stop giving up on the supergravity? Well, 10 brains in a heap, it's probably good enough to get a rough idea from supergravity. 100 brains, you go, okay, I'm good. And indeed, then there will be a problem of trying to fit them all on the torus, but
No, you're talking about, well, but those, if you've got 10 brains on top of each other, then I would claim that you have some kind of 2-0 theory or equivalent that you have to deal with for coincident five brains as
yes, and the
governing some
supergravity is
large
going to get
piece of
some
infrared
limited
physics.
knowledge of that. But one thing you can do is you can look at M2's M5's meeting. The intersection gives you a beautiful conformal field theory, and you can do the holography of that beautiful conformal field theory. Not much of it has been done. It's this weird conformal field theory, but I think we can put momentum waves on the solutions that Doka have, and we can start doing on every single such intersection what one has done for the superstratum and the precision holography of superstrata. I don't think that's necessarily a bad idea.
Mhm.
So that's what I hope we can do. The six-dimensional story has run its course. We have to start looking at the
I
dissection.
think there's something more. ADS-CFT tells us that, even if you have a 2,0 theory on the fibrins, when you have the number of fibrins which is large enough, this 2,0 is described locally by some ADS7 cross S4. And, that's basically, so here we'll have a system of, brains and, some other two brains in between them and so on and so forth. They'll blow up some bubbles and there'll be some geometric transitions and you'll get some nice ADSs in the infrared.
Yep.
So this black hole phase will have some nice infrared. Maybe there'll be super conformal phases. Maybe it'll look like a confining theory. We don't know.
Well,
But I think it's quite an interesting
the M2
physics, which you
intersection.
cannot get from the brains, which you cannot get from the brain intersection. In the brain intersection, non-back reaction, you just see some sources in flat space. You don't see any of this nice phenomena.
So one of the things we discovered in the brain intersections of the M2s, M5s is this mohawk structure. And I think that each of the spikes of the mohawk separately can carry a momentum wave. So you can partition, even within that ADS3, you can partition problem momentum in different parts of that solution. I don't know whether it's true or not, but that's kind of what I'd like to do, see if it'll work.
No, but we haven't been able to write such a solution, right?
No, not yet. I think it's possible, but it remains to be seen. I mean, I guess the question I'm asking is, you painted a nice picture of what the non-abelian stuff is, but I bet you a whole chunk of it can be geometrized.
That would be very nice.
So coherent limit. And the best I can hope for is that it's, the worst case from my perspective is that I think we'll be able to do it exactly for a single intersection. It's when you start combining intersections that the supersymmetry may break down, be broken. There might, it's like the W brain. If you have one of them, it can be supersymmetric. But the minute you put in a neighborhood of another one, it can only be supersymmetric in the sort of zero size.
But that will not happen in the Loonis system. The Loonis system is guaranteed to work. So even if you have multiple intersections, because it's a system with 8 supercharges and some more Ampere equation, the Loonis system is guaranteed to work. So I don't think there'll be any problem. In the W brains, you didn't have a supersymmetric system underlying it. A single one was supersymmetric almost by accident. And then two of them were not. But there's no underlying supersymmetric system. And in here, for the supermaze, there will be some M5, some M2s. In between them, there's a Loonis system. There's a single function satisfying some more Ampere with some boundary conditions. You can give it to a mathematician who will prove there's a solution. You cannot have any supersymmetry broken. You just have to solve more Ampere with some boundary conditions. Maybe there's an obstruction. Maybe you can say that.
Joseph, I agree with that statement, but once you start loading it with momentum waves, then it's possible the momentum waves on each intersection will hate each other. It's possible.
Oh, it's a linear system. It's a linear system. Why would they hate each other?
For the same reason that multi-centered multi-dimensional bubble solutions, so multi-centered bubble solutions apparently get lifted. So I can imagine that these will be lifted if they're multi-centered.
No, they cannot be lifted. Again, they're all at the zero angular momentum. So all the arguments about lifting have to do with going in a moduli space and so on. Those are all going to be on the same on top of each other on the torus. So they're the Higgs branch states clearly by construction, so they cannot be lifted.
On this subject. We can argue back and forth, but we just have to calculate. Anyway, do we want to call it a day? Thank you, Emil. That was fantastic.
Thanks a lot. Yeah.
Good for an argument. Fantastic.
Yeah, thanks, Emil. Thanks a lot.
Sure.
Okay, so see, we have next one. Next things are on Wednesday, right? Because we've got
Next thing is on Wednesday. Yes, we have two people talking about fortuitous states. We have Masaki or Marshall Hughes, and we have Huan Yu Yang who are going to talk about fortuitous states and the supergravity version thereof. So that would be.
sounds great.
Nick, don't stop the Zoom.
How do I, let's see.
Or Emil, maybe you can stop the Zoom so that the YouTube stops as well.